Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we're going to discuss application of the canonical distribution. Let me adjust this. Let me encirculate. This is our today's topic, application of the canonical distribution. In the last lecture, we discussed the canonical distribution. Let me remind you, P sub r is equal to C. C is a constant of proportionality, exponential, e raised to power minus beta E sub r. So this is the probability distribution called canonical distribution, and the ensemble defined through this probability distribution is the canonical ensemble. Now this canonical distribution, when we use it, we apply it to situations where it can be used. It yields very important results, the results which are physically very important. It leads us to those results. We are going to discuss one application of this canonical distribution, that is paramagnetism. Let me write here paramagnetism. We will see that making use of canonical distribution, we can obtain the results which we already know from our previous classes pertaining to this phenomenon of paramagnetism. So consider a substance which contains N naught magnetic atoms per unit volume. So we take a substance which contains N naught magnetic atoms per unit volume. So this N naught is the number density of the magnetic atoms in the substance under consideration. What we do, we place this, so we have some region of space where we produce magnetic field. Let these lines represent some magnetic field. And we represent this magnetic field by, I will change the color of my ink. I will represent this magnetic field by H vector, right? We represent it also by a B vector, so don't get confused. As I told you in the previous lectures, you need to define your symbols and be cautious about those. symbols. You have to define each and every symbol which you use. So N naught is the number of magnetic atoms per unit volume in the substance under consideration, and we are placing this substance in an external magnetic field H. So let me show some simple figure. So we have some substance, and that substance contains atoms. We're placing this, let me write it here. This is the substance under question or consideration. So we are placing this substance in the external magnetic field H, and this substance contains N naught magnetic atoms per unit volume. We assume that each atom has spin half. Each atom has spin half. So that will correspond to one unpaired electron. So in the atom, there will be one unpaired electron. So overall atom will have spin half, and an intrinsic magnetic moment of the atom, let that be mu. So let mu be the intrinsic magnetic moment of the atom. So let mu be the intrinsic magnetic moment of the atom. Remember, the magnetic moment is a vector quantity, and it gives the measure of the magnetism pertaining to some magnet. Every magnet has some magnetic moment. Now remember, we are talking of here intrinsic magnetic moment, that is which is due to the spin. We are not talking of the motion of the atom. There is another variety of magnetic moment which is called orbital magnetic moment. We are not considering that. We are considering the magnetic moment which is intrinsic to the atom due to its spin. Now we have already discussed this in an example in the previous lectures, that when we have a spin half particle, then in quantum mechanical description, this magnetic moment of this particle here, the atom, can then point either parallel or antiparallel to the external magnetic field H. So let me add page. Okay. So in quantum mechanical description, the magnetic moment of each atom, let me write it, the magnetic moment of each atom can point either parallel or anti-parallel to the external magnetic field, to the external magnetic field H. That is, it can exist in two states. Now, we have to first understand how we are going to use this canonical distribution. Now, if the substance is at absolute temperature T, is at absolute temperature T, what we want to figure out what is the mean magnetic, let me write it first. What is the mean magnetic moment mean magnetic moment, we know that by mu bar, but I write subscript h, which denotes in the direction of the external field h of such an atom. Understand the question. Let me check it. So we assume the absolute temperature of the substance is T. Now what we want to figure out, what is the mean or average magnetic moment mu bar sub h in the direction of the applied magnetic field H of such an atom. So when we talk of this mean, that means we're considering the statistical method. Now see how it is a canonical ensemble. We assume that each atom interacts only weakly with the other atoms and with the other degrees of freedom of the substance. So it is then permissible to focus attention on a single atom as a small system under consideration and to regard all the other atoms and other degrees of freedom as constituting a heat reservoir. Understand this point. So we're considering single atom as a system and all other atoms in the substance or other degrees of freedom which are relevant here that form the heat reservoir. So our atom, which is our system, single atom, is same as the system A, which we considered last time, and A dash was our heat reservoir. So here A dash is all other atoms and all other degrees of freedom. So that's why the ensemble which we construct here pertaining to this atom, single atom, which is our system, is a canonical ensemble because it is in thermal contact with the reservoir formed by the other atoms at temperature T. I hope it's clear to you. So let us move now. As I told you, each atom can be in two possible states. We label them with plus. Plus state is the state where spin points up, spin points up. By that we mean that the magnetic moment of the atom is parallel to H. And another state in which the atom can exist, we call that minus state, which we call when spin points down. That is when the magnetic moment of the atom is anti-parallel to H. Right? So we have these two states. Now, in plus state, the atomic magnetic moment mu is parallel to H. It is parallel to H. So the component of the magnetic moment which is in the direction of H is full mu. Mu H is mu. And the corresponding magnetic energy of the atom we call epsilon plus is minus mu H. What is it? It is magnetic energy of the atom when it is in plus state. Where from I have obtained it? Remember this relation. When you place a magnetic moment in external magnetic field, you have expression U is equal to minus mu dot H. So we express this as a dot product. When mu is parallel to H, the energy becomes minus mu H because cos 0 is 1. So when the atomic magnet is parallel to H, the magnetic moment in the direction of H is mu, and the magnetic energy of the atom in this plus state, which we call spin up state, is minus mu H. Let me encircle it. Right? E epsilon plus is minus mu H. Therefore, the probability of finding the atom in this state in this state is which state? Spin up state or plus state when mu is parallel to H. Since we are using canonical distribution, we have defined canonical ensemble. So the probability of finding the atom in this plus state, P plus, is simply C, constant of proportionality, e raised power minus beta epsilon H. Remember the previous relation pertaining to canonical distribution. We're simply replacing ER. Here state was specified by R. In our case, state is specified by plus and minus. So we have made use of this distribution here. So P plus is C e raised power minus beta epsilon plus, which can be written as C equal to C times e raised power beta mu h. I name it equation first. So let me encircle it with this color, right? This is our equation first. We have simply here substituted for epsilon plus as minus mu h. So we got it. C e raised power beta mu h. And we know C is a constant of proportionality, which is independent of the state, and beta is 1 by kt, or you can write it kt raised by minus 1, where k is the Boltzmann constant. Now this is the state of lower energy. Remember, when mu is in the direction of magnetic field, it has least energy among all other orientations. So this is the state plus state, that is when mu is parallel to h, is the state of lower energy, and thus the state in which this is the state in which the atom is more likely to be found. I repeat, since this state, that is plus state or spin up state, that is when mu is parallel to h, is the state of lower energy, this is the state in which the atom is more likely to be found. Let us move now to other state. Now in the minus state, mu is antiparallel, mu is antiparallel to h, so that what is mu h, magnetic moment in the direction of h, is minus mu, right? And the corresponding energy, magnetic energy of the atom, sorry, it is E minus, epsilon minus, it is plus mu h. Let me encircle it. So when the atom is in negative state, that is mu is antiparallel to h, the magnetic moment of the atom in the direction of h is minus mu, and the corresponding energy of the atom due to this we call magnetic energy, epsilon minus, is plus mu h, because of the relation which discussed. And mu is antiparallel to h, we have here cos 180 degree, which is minus 1, overall it will become plus. So we have this magnetic energy here. So the probability of finding the atom in this state, that is this negative state, we can write as P minus is equal to C e raised power minus beta epsilon minus, which can be written as C e raised power minus beta mu h. Let me name it second, and let me encircle it. Let me use green color. So P minus is C e raised power minus beta epsilon minus, which is C e raised power minus beta mu h, because epsilon minus is plus mu h. This is the state of higher energy, because when the magnetic moment is anti-parallel to the magnetic field, it has the highest energy. So it's the state of higher energy. And thus this is the state in which the atom is less likely to be found. So plus state is more likely and minus state is less likely, right? Because of the energy consideration. So as I told you, since the first state, that is the plus state, where mu is parallel to h, is more probable, it is clear that the mean magnetic moment must point in the direction of the external field. When we take the average over the ensemble which we constructed, I'm saying since a plus state is more probable, mean magnetic moment must point in the direction of external field. We denote that by mu bar h. What is this? It is the mean magnetic moment. Mean magnetic moment of our atom under question. Mean magnetic moment, which is ultimately in the direction of h of the atom. Right? We write subscript h to indicate that it is in the direction of external field h. Right? Now, by virtue of equations 1 and 2, let me write it in the next page, or I should say from equations first and second, we can see that the significant parameter in this problem under question is beta mu h, which I can write as mu h by kt, and we write it as y. Let me encircle it here. We are seeing in our discussion the significant parameter, as we see from equations 1 and 2, which we wrote for P minus and P plus. The significant parameter is this beta mu h. This beta mu h, which is equal to mu h by kt, we can simply write it or designate it by y. If you see what it measures the ratio of the typical magnetic energy to the typical thermal energy. Mu h here is the typical magnetic energy, and this kt is the thermal energy. Right? This is the thermal energy. So y is the ratio of these two things. Now it is apparent that if T is large, that is if y is much less than 1. Remember, when T is large, that means y is very small compared to 1. The probability that mu is parallel to h is almost the same as that of its being anti-parallel to H. So in this case, mu is almost completely randomly oriented, and the average magnetic moment in the direction of H per atom is approximately 0. Think about this. Let me write it here. This is 0. Let me first consider the next situation. Now, if T is very small, when T is very small, that is Y is much greater than 1, then it is much more probable that the magnetic moment mu is parallel to H rather than anti-parallel to it. So in this case, the average magnetic moment in the direction of field is approximately mu. Let me change the color here. Let me write here. Think about this. Let me get my pen back. Think about this. Now we have discussed this situation qualitatively. So what should happen at high temperature and low temperature? Now these qualitative conclusions can be readily made quantitative by actually calculating the mean value of the magnetic moment. So let us calculate. Let us calculate mu h bar. I will use here blue color. So we will calculate this average magnetic moment in the direction of H. So we can write mu h bar as P plus mu plus P minus mu over P plus P minus, which is equal to mu times e raised power beta mu h minus e raised power minus beta mu h over e raised power beta mu h. This is beta here. Let me write it neatly, I think. Beta mu h plus e raised power minus beta mu h. Check this. Is easy. So check this. So mu h bar is P plus mu, because in that state probability is P plus and the value is mu, plus P minus times mu minus mu over P plus and plus P minus. We are dividing the sum of the states. So it is mu times e raised power beta mu h minus e raised power minus beta mu h over e raised power beta mu h plus e raised power minus beta mu h. So I can write it, I can use the definition of the hyperbolic tan. So I can write here it as or mu h bar is equal to mu tan hyperbolic of mu h by kt. Let me name it equation third. Let me encircle this with this color. This is my equation third. I have used previous equations in p plus p minus. You can check it. So it is mu times tan hyperbolic of mu h by kt, where we have used the definition of hyperbolic tangent using the definition of hyperbolic tangent tan hyperbolic is equal to e raised power y minus, sorry, tan hyperbolic of y is e raised power y minus e raised power minus y over e raised power y plus e raised power minus y. This is the definition of tan hyperbolic of y. We have made use of it. E raised power y minus e raised power minus y over e raised power y plus e raised power minus y. Now remember our y is this beta mu h, which is mu h by kt. So let's move. Now we define a thing called magnetization. You might be knowing it from your previous classes. What is magnetization of the substance under consideration? We denote it by m naught bar. It is simply mean magnetic moment per unit volume. So it is by definition the mean magnetic moment per unit volume of this substance under consideration. So it will be simply written as its name suggests, m naught bar is equal to n naught times mu h bar. Let me name it 4. Remember, n naught is the number of magnetic atoms in our substance under consideration in the unit volume, and mu h bar is the average magnetic moment per atom. So the magnetization is simply n naught times μh bar. So this magnetization will also be in the direction of the applied magnetic field H. Now one can easily check that μh bar exhibits the behavior which we discussed qualitatively before calculating it. See how. If y is much less than 1, then e raised power y is 1 plus y plus so on, and e raised power minus y is 1 minus y plus so on. Remember the exponential series. Let me use this color. We have this exponential series. E raised power x is 1 plus x plus x squared by 2 factorial plus x cubed by 3 factorial plus so on. So we're making use of it here, where we have e raised power y and e raised power minus y, but our y is beta mu h or mu h by kt. So we are saying when y is, but we are writing this exponential series in this limit when y is much less than 1. So when y is much less than 1, then e raised power y is 1 plus y plus so on, and e raised power minus y is 1 minus y plus then so on. And for y much less than 1, tan hyperbolic of y is equal to 1 plus y plus so on, then minus 1 minus y plus so on over 2, which is just y. Check it. Me right here. Check this. When y is much less than 1, tan hyperbolic y is 1 plus y plus so on minus 1 minus y plus so on over 2. We're using this expression. This one definition of tan hyperbolic. So it's just y. On the other hand, if y is much greater than 1, then oh, let me get my pen back. Then e raised power y is much greater than e raised power minus y. Therefore, for y much greater than 1, tan hyperbolic of y is just 1. Check this out. When y is much greater than 1, e raised per y is much greater than e raised per minus y. So for y much greater than 1, tan hyperbolic y is equal to 1. Thus equation 3, I will write this, but leads to this for, remember our y is mu h by kt. Mu h by kt, when it is much less than 1, our mu h bar is mu square h by kt. I name it equation 5a, and I will use another color here. For mu h by kt much greater than 1, we get mu h bar is equal to mu. I name this equation 5b. Let me write it neatly. This is my 5b. Let me encircle these results first in red color. So this is one result. This is another result. Let me check them. For mu h by kt much less than 1, we have a mu h bar is mu square h by kt, it's my 5a, and for mu h by kt much greater than 1, mu h bar is mu, this 5b, and this is equation 3, which is leading us to this limiting behavior when we use it the above conditions. Our equation 3 is this. You will check this at home. We have put restriction on this tan hyperbolic of this thing, which we represented by y, for y much less than 1 and y much greater than 1, right? So check it out. Now, by equation 4, by equation 4 and equation 5a, it follows. What follows? This follows. If mu h by kt is much less than 1, then our magnetization is proportional to h, and the constant of proportionality is written by this Greek letter. It is called chi, I think. We'll check it. This is my equation 6, where this chi, check it, its name, is a constant of proportionality independent of h independent of H is a constant of proportionality independent of H, and it has a name. It is called magnetic susceptibility of the substance. Magnetic susceptibility of the substance. This magnetic susceptibility of the substance. Let me first check it. 4 and 5a follows if mu h by kt is much less than 1. This magnetization is proportional to h. Constant of proportionality is called the magnetic susceptibility. Let me encircle this equation. You will check every piece of the lecture yourself. It is I'm saying equation 4 and 5a. This is my 5a and this is my 4. That is this. Let me add the page. Now equation 5a, or I should say from equation 5a, we can express chi, there's a magnetic susceptibility, in terms of the microscopic quantities. So let me write it from equation 5a, we can write chi equal to n naught mu square by kt. I name it equation 7. You will check it. Chi is magnetic susceptibility is written as n naught mu square by kt. See, this equation 7 expresses magnetic susceptibility of the substance in terms of the microscopic quantities. So you can see from 7, this chi is inversely proportional to T. Magnetic susceptibility is proportional to T raised power minus 1. Now this result has a name. It's called Curie's law in magnetism. Chi is inversely proportional to the temperature of the substance. Now, on the other hand, if mu h by kt is much greater than 1, we get magnetization is, or I should say, approaches to n naught mu. Let me name it 8 and let me encircle it. You will check this. So what we said qualitatively, we have expressed that quantitatively also. We said that when first call this qualitatively, when mu h by kt, that is when t is small, right? Then the average magnetic moment will become mu, then the magnetization will become n naught times mu, right? And for the previous situation, that is this, where is this? Our magnetization was chi times T. So for larger temperature, that's when this ratio is very small compared to this, there comes this proportionality with H, and the sky contains these parameters and not mu by kt. So you will check it and compare it with this discussion which we said before talking, before calculating actually the mu h bar, right? I think here. So you will compare that. This one. When I told you that when t is large, that is y is much less than 1, then mu h bar is approximately 0. And when t is small, y is much greater than 1, this mu h is mu bar, mu h bar is mu. So the second condition is this one, the last one, when we said the magnetization is n naught times mu, and the first situation corresponds to other condition, right? This one. You will check it and compare the qualitative discussion with the quantitative calculations. So in this case, when mu h is mu h by kt is much larger than 1, magnetization approaches n naught mu. In this situation, this magnetization, that is for this limit, this magnetization becomes independent of H and equal to the maximum or saturation magnetization of the substance. Remember, this N naught mu is the maximum or saturation magnetization, right, of the substance which the substance can exhibit. Now, this complete dependence of this magnetization on temperature and magnetic field H can be depicted in the figure. So let me show this, try to construct this diagram. As I told you, it is difficult to hold this magnetic pen. I think I can draw this line here. This line. This is my one line. Okay. Let me take it down. This is my one line. Let me use this feature again. Okay. Let me get my pen back. So on this side, we will plot magnetization over N naught mu, that is ratio of magnetization to its saturation value, right? So let me let this be here 0. This is my 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, it is 1.0. So here we have this limit expressed by equation 8. When the magnetization approaches the saturation value, let me draw on this side first. I will draw or first label this horizontal axis. So on this side, what I am plotting this, the parameter, which was denoted by y, mu h by kt. So here it is 1, then here it is 2, here it is 3, right? So I need, okay, I will draw it by hand. Let me use another color here. Let me try to draw the curve. I will draw it in brown. It goes approximately like this. So first it has a linear behavior, then it goes like this. You can see this diagram in any text. In this region, we have this linear relationship. Here, my magnetization m naught mu, sorry, m naught bar is proportional to h. So this is the figure, I name it figure 1, which shows the dependence of magnetization m naught bar on the applied magnetic field, that is H, and temperature T for non-interacting, remember we first at the start said the interaction is weak. Magnetic atoms of spin half and magnetic moment mu. So this is the dependence of mu bar on H and T for non-interacting magnetic atoms of spin half and mu. So this completes our discussion of paramagnetism. So before leaving you, I will just summarize the lecture. So today we used this canonical distribution to establish some results pertaining to paramagnetism. So we put this paramagnetic substance inside the magnetic field, and then we said qualitatively what should happen. Then using canonical distribution, uh, first we establish it, how we can use this canonical distribution. We said that our atom in question can be taken as a system, and all other atoms of the substance at temperature T and other degrees of freedom can be treated as a heat reservoir. So we justified the usage of canonical distribution. Then we talked about the average magnetic moment per atom qualitatively at large T and small t. Then we calculated it and got our quantitative results. And I told you to check everything and do it at home. It's all for today. Thank you. Assalamu alaikum.